Assessing the quality of observations and estimates. In this chapter, we're going to cover 6 items, which you can see in the slide. First, we're going to have a discussion, an overview discussion on measurement and errors. Then, we're going to talk about the concept of probability density function and histogram. We are going then to introduce the idea of statistical testing, the basic theory behind it, and then we're going to look into actual application of that in the univariate testing, and in the multivariate analysis. Univariate testing is tests that we do, the statistical tests or quality control, before the estimation process takes place. So before the least squares adjustment, for example. And we are going to look at specific tests which are the most common that we face in professional life. Tests for outliers, testing the shape of the observation's probability density function, test of the mean, and test of the standard deviation. After the adjustment, we have then parameters, residuals, and we have the a posteriori variance factor. We can test all of them. So we can test the shape of the residuals and residual outliers. We can test, we test the shape of the residuals, and we can test for residual outliers. These are 2 different tests. We can test the a posteriori variance factor, and we're going to see, to have a good discussion, we need to have a good understanding of the meaning of this test when we compare the statistical equivalence between the a priori and the a posteriori variance factor. And then we are going to finalize the tests by talking about tests that can be performed on the estimated parameters. We will complete the chapter discussing the very interesting idea of expansion factors, what they really represent, and how we can make good use of them. The overall learning objectives are to identify the various situations in which statistical tests can be applied and assess the quality of observations and least squares estimates using statistical testing as tool. We desire to determine the true value of a particular quantity. In most instances, we can only do that by measuring it. After performing the measurement, we realize that the measurements are subject to some variation, either measuring it several times or measuring it with different instruments. The measures will be slightly different, sometimes even very different. The variations in measurements are due to the instrument used, to the environment in which the measurements take place, or even due to human failure. Variation in measurements is a natural phenomenon, even if conditions are the same. The measurement or observation must be considered as a random variable. A variable is understood as a quantity or function that may assume any given value or set of values. A random variable is the outcome of a random process. In this case, the random process is the data collection and the random variable the observations themselves. We shall use the words random and stochastic as synonyms, referring to either random or stochastic variations and random or stochastic processes. We seek a true value of a quantity of interest, but all we can get is an estimate of the true value. We must expect difference, errors, between a measured value of a quantity and its true value, whatever it may be. Error does not mean that something is wrong, just that it is different, except for a blunder. We can say that there is an error, E, in an observation, L, by computing the error as the difference between the observation and its true value. So the symbol L with the two hats represents the true value of the observation. We most often never know the true value of the observation. The best we can get is an estimate, which we represent as L hat. Then we use the residuals to express the variations in the measure. And the residuals are going to be defined as the difference between the estimate and the measurement. An observation is a random or stochastic variable because it contains error components having random behavior. While a systematic error is dealt with mathematically by means of functional relationships or model, a random variable requires a probability model. Therefore, we deal with a stochastic model and a functional or deterministic model. The meaning of deterministic is that a quantity can be determined correctly by means of an exact formula. The meaning of stochastic can be twofold. It may either indicate the opposite to deterministic, or it may indicate something we are not willing to model deterministically. As seen elsewhere, there are three types of errors: gross errors, systematic errors, and random errors. Gross errors, also called accidental errors or blunders, are due to blunders or mistakes of a careless observer or the malfunction of an instrument. For example, recording 13 instead of 31, or keying in the wrong coordinates for a reference GNSS receiver are due to the observer, but a cycle slip is due to an instantaneous malfunction of a GNSS receiver. Systematic errors are the ones that follow a certain functional deterministic relationship and most of the time can be modeled. For example, the effect of temperature on a measuring tape or a defect in the internal software of a total station. Random errors are what is left after all known blunders and systematic errors are removed. There is a difference between an observable and an observation. An observable is the quantity being observed, such as a distance or an angle, whereas an observation is the actual numerical value associated with the observable. A measurement process yields a series of observations in time or space. A series of observations, L bar, can be decomposed as L bar equals to L double hat, which is the true value of the quantity, plus P. P represents the systematic component that can predict it in a deterministic way, minus V minus S, where V and S are residuals, but they are different. V is the statistically independent residual. In other words, its covariance matrix is diagonal, and S is the statistically dependent residual, and its covariance matrix is fully populated. Continue with the equation. We can also say that L bar equals to T bar minus R bar, and well, bar, I mean underline. And what we have here is the term T represents the trend. So the trend will be the first two terms of this expression. So these here is the trend. Trend is the true or expected value plus the systematic component. And then we have the residuals R, which can be understood as these two terms put together. What we do in general in least squares adjustment is we consider the systematic component to be equal to 0. In other words, any systematic effect has been removed before going to the adjustment. If P is different from 0, we can make use of it in the so-called analysis of trend, which is a subject of another chapter. Also, in our discussions, we make no difference between the residuals, the statistically independent and the statistically independent residuals. We just put them together, so which means that our residuals are they have a fully populated covariance matrix. They are statistically dependent. And a study that can be made separating these two types of residuals is done under a topic that is known as collocation. Considering P equals to 0 and the two components of the residual, V and S, put together, represented by R, what we have is the expression L, the observation L, equals to the true value minus the residual. The thing is that we don't know, in most times, in most cases, we don't know the true value. The best we can do is to deal with its estimate. Therefore, we can replace L double bar by, L double hat by L hat, and we have the expression that is similar to what we have seen before, that the observations, they are equal to the estimate minus the residual. In other words, we can define residuals as being the difference between the observation and true value. If we follow the parametric model, we can rewrite now the equation for the observation as L equals to AX. So A is the design matrix, X is the parameter vector, which then, if we replace, will result in the relationship between, explicit relationship between AX and the difference between the true value minus the residual. So what is interesting to look at here is that we this expression, let me go here, let me get a color. Okay, all right. It says here in the end, the true value R cannot be determined, just estimated by R hat, which is true. Because we need the estimate L hat, okay, to compute R hat. So the thing, what I want to emphasize here, which is something very interesting, is that both R and L are stochastic. They're random. So the observation, okay, and the residual, they are stochastic. But if you look at this term now, this equation, what we have is the left-hand side is stochastic, but the parameters, okay, the parameters, they are here, the parameters. They can relate to the observation. Okay, we can relate parameters and observations by means of the design matrix. So we can write down, it is interesting because what we have is L, okay, we can call these observation space. So there is a space where live the observations, okay, and we have now equals to A X. X, the parameters are in the, oops, this is wrong. Parameter space. So how can we relate the parameter space with the observation space by means of the design matrix? Okay, so the design matrix, it transforms let me write differently here, not transform, but it relates parameter space and observation space. So what we have in the color here, color, gonna get this one. So what we have in here, okay, a series of quantities that are is called stochastic, the observations and residuals. This figure here tries to show the relationship between observation, true value, and estimate. We have in red the true values of the observations. Okay, so the observation, the true value is 5. Okay, so at every epoch here, 1, 2, 3, all the way to 10, we have observations of value 5. That's the true value. That's the L double hat. But we only, okay, the observations that we have, the observation that we have are here. Okay, these are the actual observations. These are the L values. Okay, so L, the actual observations, are in green. And the estimates, I'm just representing the estimates. There are 5, slightly larger than 5. They are represented in blue. So the representation of the residual, graphical representation of the residual, one of them, is the difference, the vertical difference in here between the observation L and the true value L hat. Okay, so we can say that ideally the observation is going to be the true value, but it's not. We would like that the observation would be the true value minus its random variation, the random variation, the observation that is represented by the residual, but it's not. Most often, because we don't know the true value, most often we will say that the observation is the difference between an estimate of the true value, L hat, and the residual. Okay, so that's why we define the residual as L hat minus L to distinguish from an error, which is L minus L hat. So this is the part 1 of quality control.